Hello everyone. In this pre-lecture we're going to solve the time-independent Schrodinger equation for the first time. We've been working on solving the full Schrodinger equation, and we've developed this time-independent Schrodinger equations, h hat psi of x is equal to E psi of x. H is the Hamiltonian. So if I write this out in full, this is minus h bar squared over 2m psi double prime of x plus v of x, the potential function, psi of x is equal to E times psi of x. That's what we call the time-independent Schrodinger equation, T-I-S-E, time-independent Schrodinger equation. And I claim to you that if we were able to solve this for some value of E, where E is the energy, then we know how to solve the full Schrodinger equation because my full time-dependent wave function, psi of x and t, was psi of x times e to the minus I e t over h bar. So now the problem comes, how do I solve this equation? I can't go any further without specifying what is the potential. What potential well is my particle experiencing? What forces, if you want to think about it in a classical sense, is the particle experiencing? So we can't go any further without specifying that. So we're going to use the simplest possible setup for the potential well, which is called the infinite square well. And I'll show you a picture in just a second. So, but you should think about this as just a particle stuck in a box. So the box is of length L. It traps the particle in the box, but otherwise nothing interesting is happening inside the box. The particle has no forces in a classical sense. It doesn't gain or lose potential energy on one side of the box compared to the other. It's free to move inside the box, but it cannot escape the box. So this is going to be our potential energy diagram for that setup. You can see the box is length L, so it ranges from x equals 0 to x equals L. Outside the box, at x negative or x bigger than L, V is equal to infinity, which means the potential is infinity, meaning the particle cannot exist in that space. And then inside the box, the potential is 0, meaning the particle feels no forces or anything inside there, so it's free to move. So if you want to put a mathematical equation with that, your potential energy as a function of x is piecewise. So it's 0 for 0 less than or equal to x less than or equal to L, and it's infinity otherwise. We would like to know what is the wave function of the particle inside that box. So we got to go back to our time-independent Schrodinger equation, which looks like this. Now, outside the box, psi is going to be equal to 0 out here. So whenever the potential is infinity, the particle can't exist out here, so psi will be 0. But we want to know what is happening inside the box. Inside the box, the potential is equal to 0, so this term is equal to 0. And I have a differential equation which looks like this. I can put all these constants onto the other side. Minus 2me over h bar squared times psi of x. So that's a differential equation which I'm trying to solve for the wave function inside the box. Let me clean up the notation a little bit. So remember, m is the mass of the particle, E is the energy of the particle, and h bar is a constant. Remember, this is a massive particle, so E is p squared over 2m, right? If I write it in terms of momentum. And we also have the de Broglie wavelength, p is equal to h over lambda for the quantum particle, which has some kind of wavelength or wave nature to it. So I can combine these two things, and I have. So let me take this and substitute it in here, just to make this look a little bit nicer. So let me put in here minus 2m over h bar squared, and then put in what is E, which is h squared over 2m lambda squared times psi of x. Okay. The 2m's cancel, and I have h squared over h bar squared. Remember, h bar is h over 2 pi, so this becomes minus 2 pi over lambda squared times psi of x. And then typically, we call this 2 pi over lambda is k, the wave number, so this is going to be k squared. So all in all, with all of these manipulations, remembering that k is 2 pi over lambda, I can rewrite my time-independent Schrodinger equation in the following way. For this potential, psi double prime of x is minus k squared times psi of x. And you'll just have to remember that k squared is 2me over h bar squared, which is 2 pi over the wavelength of the particle squared. All right, so now we have this equation. K is a constant related to the energy of the particle. We have to think about solving it. So I'm going to ask you a poll question here. This is the differential equation that we're trying to solve. Psi double prime is minus k squared psi. K is a positive constant related to the energy of the particle. So a little bit of review of differential equations. Which of these choices is the general solution to that differential equation? So you have a few choices, A, B, C, D, and then E is saying that more than one of the above is okay. Why don't you go ahead and pause the video, see if you can settle on one of these answers before going further. Okay, have you made your choice? The correct answer to that one is actually E. Both C and D are possible solutions to this differential equation. What is this differential equation saying? It's saying I'm looking for a function psi where if I take two derivatives of it, I get the function back again multiplied by a negative constant. And hopefully it's not too hard to imagine that I could try some function like sine of kx. If I take derivatives of it, psi 1 prime of x, I get k cosine of kx. The k comes out front from the chain rule, and psi 1 double prime of x is minus k squared, again, factor of k from the chain rule times sine of kx, which is minus k squared times what I started with. So that satisfies the differential equation. You can check that cosine also works. So psi 2 of x, if you tried cosine of kx, take derivatives of that, the general solution is found as an arbitrary combination of those two. So psi of x will be some constant a sine of kx plus some other constant b times the cosine of kx. A and b are arbitrary constants. So why is C also a solution? Because remember Euler's formula, e to the I kx is cosine kx plus I sine kx. So I can always trade these sines and cosines for complex exponentials. So I could also write it this way. I could say psi of x. Maybe I should write some different constants here, e to the I kx plus d e to the minus I kx. Both of those are acceptable. They're basically equivalent with different arbitrary constants in front. When do I use one over the other? It depends on the problem. Sometimes the first formulation is more useful than the second formulation, and we'll see both of those cases in this class. Okay, so now we know outside the well the wave function is 0 on either side, and inside the well I have some combination of sines and cosines. Now we aren't done because we have boundary conditions on psi. The boundary conditions are that psi must be continuous. So if the wave function is 0 at the outside the box, that means that the wave function needs to go to 0 at the edges of the box in order to be continuous through this entire range. So that means that psi of 0 must be equal to 0 so that it matches the 0 wave function on the left side, and psi of L has to be equal to 0 on the right side so that this wave function on this edge of the box here matches 0 outside the box. So let's apply that to our wave function here. Psi of 0 equals to 0 means that 0 is equal to a sine of k times 0, which is 0, plus b cosine of k times 0, which is equal to 1. And this tells me that b is equal to 0. Okay. So in fact, it can only be made up of a sine function. So this is gone. Now let's apply the second boundary condition, which is psi of L is equal to 0. So that means that 0 must be equal to a times the sine of k times L. Things are starting to look a little ominous here because you're thinking, okay, one way to solve this is just to have a equals to 0, but if a equals to 0, psi itself is 0 and nothing interesting happens inside. There's one way out of this, is that as long as I keep a non-zero in order to keep this term there, so I have some interesting solution, it could be that the argument of the sine function is such that the sine vanishes. So we must have k times L must be equal to some multiple of pi. In other words, there's two ways to satisfy this. Either a could be 0, which would be boring, because then nothing interesting would be happening, or k must take on some particular values so that the sine function itself vanishes. So this is really sort of unexpected, that apparently there's only certain values of k which are allowed. Basically, k times L has to equal n times pi. So we have our solutions for the infinite square well. Apparently we can solve the time-independent Schrodinger equation and meet the boundary conditions that psi is continuous if psi is a sine function times some arbitrary constant. But the argument of the sine function kn has to have certain values. So kn times L must be equal to n pi. What does this mean? So let's go back and remind ourselves k was 2 pi over lambda, right? Which I can solve for lambda. Lambda n is equal to 2L over n. So if I think about my particle as having a wavelength, apparently only certain wavelengths are allowed, which satisfy this. And this might look familiar to you from your earlier physics courses. If I look at my box, which is a length from 0 to L, if n is equal to 1, my wavelength is 2L, so that looks something like this. This is going to be n equals 1. If I look at n equals 2, my wave function looks something like this. The wavelength is equal to L. And you can continue drawing these kinds of things. You see, these are standing waves that fit into the box of side length L. So my wave function is just sine functions with wavelengths that divide the length of the box into integer number of half wavelengths. So here there's 1 half wavelength, here there's 2 half wavelengths, n equals 3 would be 3 half wavelengths, and so on. I can use what we know about k to write in here now n pi x over L, because I use the fact that kn was n pi over L. And now let's remind ourselves, what does this mean about the energy? Remember that k squared was 2me over h bar squared. And we said that apparently only certain values of k are allowed, which means that only certain values of energy are going to be allowed here. And which ones are there? They're the ones that satisfy this, is n pi over L. So if I substitute that in here, I get that n squared, pi squared, over L squared is equal to 2m e n over h bar squared. And I can solve this for the energy. En is equal to n squared pi squared h bar squared over 2m L squared. So we have our first solutions to the time-independent Schrodinger equation. We were looking for one solution and we end up with an infinite number of them. The wave function are these sine waves, which have wavelengths which fit into the box. And only certain wavelengths are allowed, which means that only certain energies are allowed. The energy of each level has to satisfy this, where n is an integer. So we have the quantization of energy, meaning unlike a classical particle which could have any energy in this box, this quantum particle can only have certain energies which satisfy this, and certain wave functions which fit exactly in this box according to a standing wave. Thanks for listening, everybody. If you found this useful, please like and subscribe.